Hi, my name is John Corrette, and on behalf of Michael Kelly, my advisor, Dr. Learman, I'll be presenting a model of surface-dependent reactions. What we are interested in modeling is a surface-dependent enzymatic reaction as follows, where we have an enzyme and zymogen species bound to a lipid surface. They bind together, and the enzyme cleaves the zymogen into some product, which we denote here as P. Current models exist for this process. However, they do not capture all the effects of being on a lipid surface, which is what we will attempt to capture by modifying our on rate K plus star. This is what typical results look like for measuring lipid-dependent reaction rates. What we have on our y-axis is the rate of factor 10A generation, which is a common clotting factor in the blood coagulation cascade. And on the x-axis, we have our lipid concentrations. And what we're seeing from this plot is that some optimal lipid concentration exists. What current mathematical models see is not an optimal value, but a monotonically increasing rate as we increase lipid concentrations. So how we're going to attempt to capture this effect is with what we can call the dartboard model. So what we have here is our lipid surface L inside the circle, and we have a bunch of enzymes and zymogens floating out in some sort of fluid phase. What will happen first is an enzyme will, like a dart, be thrown at the board, and it will bind at some random location. What we want is a zymogen to bind at a random location that is close enough to the enzyme to react. So we define this new area around the enzyme, and this is our reactivity zone. If a zymogen's in here, the reaction can occur. So if we throw two zymogens at the board, what we see is that the zymogen inside the circle is allowed to bind in green, and the one outside in red, nothing happens to it. So the one inside, the reaction occurs, and the product is kicked off back out into the fluid phase. So how we're going to capture the effect of this dartboard models in terms of probabilities by modifying the old K plus term from old mathematical models with this probability of a zymogen being near an enzyme. And we modeled this with a binomial where our probability, EB over L, is the proportion of the surface taken up by the enzyme's area, and N is the number of sites around the enzyme that are available for a zymogen to bind. And this N parameter is currently unknown. So to model this, we simulate it by converting our chemical equations to a system of ODEs in MATLAB, and we produce the production rates as we saw earlier in our data. And what we have here in blue is the old model where we do not incorporate the probability, and we see a monotonically increasing rate of factor 10A generation. However, for all values of N, we plot a couple here for you to see, we see this optimal value being produced. So our model has actually captured this effect that all models previously have not done before. And what is great about this is that our model is able to qualitatively replicate lab experiments on lipid-dependent rates in terms of behavior. And we've also produced a model that is flexible and able to adapt other reactions.